And remember, remove the videos of the people. Hello, everybody. Welcome to the workshop about fecal sludge drying. This workshop is going to be held today, 22, and tomorrow, 23 of September, from 2:15 to 5:15 South African time. Sorry, there was a change of time with respect to the brochure. But we had to offset. We have to offset the beginning of the workshop. So I introduce myself. I'm Dr. Santiago Septién Stringer. I am from the Pollution Research Group at the University of KwaZulu-Natal, and I would like to introduce you here my country group, technical group, which is led by Tracy Mupinga, which is around us, and she's going to take the minutes, and Tanaka Chatema, who is going to admit the people, to manage the entry, the out of people, and she's going to have controls of your microphone and videos. So let's going to start to give, I would like to give a background of what I'm doing this workshop, and to put you in the context. So as many people from you have to know, there are 2 billion people without access to proper sanitation, according to the World Health Organization. And this causes a lot of threats to the public health and for communities, especially for underdeveloped communities. We see that around 500 children die every day due to the lack of sanitation in sub-Saharan Africa, according to the UNICEF. And so the United Nations set the Sustainable Development Goals, and one of these goals, the number 6 to be exact, is to lead to a safe managed sanitation. And here you can see an example in the diagram of good sanitation. So we can see that there has to be a good containment. The toilet has to be a nice toilet, a decent toilet where people can do all their needs. And then in this waste, the excreta has to be contained safely. And then after that, when the pit where the excreta is accumulated is full, there has to be a system to empty it. And then after emptying it, to transport it to the fecal sludge treatment plant, was going to be treated. And after treatment, we're going to try to dispose of the sludge once it will be saved, or why not reuse it and maybe get some benefits from it. There is another concept that I would like to discuss with you, is the concept of reinvented toilet. So it is also to lead to a safe sanitation and decentralized sanitation. But here the difference is that the excreta is treated in situ. And in a reinvented toilet or toilet with in situ treatment, there is 2 components. There is the front end and the back end. The front end is the user interface, and the user interface is the one who is going to be in interaction with the user, and is going to receive all the wastes. Among the waste, we have feces, urine. This is the basic ones, but also can be water, depending on the toilet and the culture, and toilet paper. In some cultures, people use toilet paper. In other cultures, people use water, but could be a product. So after that, the toilet can lead, depends on the toilet technology. Sometimes there is separation of the waste from the source, sometimes not. But in all the case, the different streams from these toilets go to a in situ treatment. And this in situ treatment, depending on the technology, are going to lead to, first of all, and more importantly, to the disinfection of the waste. And after disinfecting the waste, there are valuable products that can get, for example, water. The water can be recirculated for reflushing, for example. We can get maybe some fertilizer, maybe we can produce electricity or get a biofuel. So there are different options that we can get it. So what is important in all this? Faecal sludge drying is very important in all this. First of all, it leads to the reduction of the mass and the volume. So we minimize the size of and the weight of the product, of the waste. And after that, this for sure is going to have benefits in the transportation and storage cost. Drying also leads to the disinfection of the waste because, first of all, many times we introduce heat that is going to destroy the cells of the pathogens, but also we're removing water, and microgens needs water to develop. So this is going to lead to a safe product. And when it's safe, we can recycle without any problem. But also drying, we will remove, by removing the water inside the waste, we're going to concentrate through its carbon content. And by concentrating its carbon content, it can be used as a biofuel later. So here we can see a fecal sludge treatment diagram. Here we can see that drying occupies a central part in the treatment of fecal sludge. Drying could be used for pre-treatment. For example, if you want to burn the fecal waste, we need to dry it before. But also drying could help to remove water for its composting or for its direct reuse in agriculture or just for disposal. And before the drying, there's also a dewatering step, which is very important because sometimes the fecal sludge is very liquid, so we need to remove the water before drying it, and otherwise it will be a very expensive process. The only way to get through this drying and dewatering will be a process where we treat the waste in an aqueous phase, for example, hydrothermal carbonization. So let's go to talk about this workshop now. Well, this workshop was done under the context of a project funded by the Bill and Melinda Gates Foundation, which is entitled Characterization of Fecal Material Behavior During Drying. The aim of this project is we want to generate useful data and knowledge to overcome technological gaps in the drying sector. And once we get all this knowledge, we try to disseminate. For example, I already made a web seminar, and now I'm doing this workshop. And the particular aim of this workshop is we want to create a dynamic communication. I invite many speakers from different backgrounds. I invite also drying specialists in the sector of sewage sludge drying. And we wanted so to create that we want to learn from the experience of each of us, that maybe we are researchers, maybe we are practitioners, maybe we come from different backgrounds. So we wanted to make a transfer of knowledge between us, and with this try to find solutions to problems that we can have. Okay, this is the program of today. So in the program of today, we first of all, now we're in the introduction of the workshop. Then we have the opening remarks. We have the luck to have Dr. Carl Hensman from the Bill and Melinda Gates Foundation, Dr. Sudhir Pillai from the Water Research Commission, and Professor Chris Buckley from Pollution Research Group from University of KwaZulu-Natal. And then after that, we're going to have some presentations. And the first presentation is just to introduce drying for the people that are not very used to that. And then after that, I'm going to present the investigation on fecal sludge drying at the pollution research group. And from there, we're going to have two presentations from my two invited drying experts in the sector of sewage sludge. First of all, with Professor Patricia Labos from France, from INSALB, and then Professor Angelique Leonard from the University of Liège in Belgium. And from there, we are going to go to presentation more for fecal sludge with a municipality point of view in South Africa. We're going to talk, then we're going to travel to Kenya, to United Kingdom to see more experience with fecal sludge. And we're going to finish with a group discussion and closure of the day. And tomorrow, we're going to have a very similar day. We're going to start with a summary of the tomorrow. And then we're going to have more presentations of this. We're going to have a presentation of a collaboration between the University of Sydney and an institution in Tanzania. Then we're going to present a very interesting technology, which is a microwave treatment of sludge using the sheet killer. And from there, we're going to learn about the experience in fecal sludge drying in a treatment plant in India by technocrats. And then we're going to see some research at Swansea University and Cranfield University and Duke University from the United States. And after this, we're going to have group discussions where we're going to finish 1 hour of group discussions where we'll try to what we learn, to tell what we learned from the presentations. If we have further questions, if somebody wants a problem that he wants to raise, it's a moment to talk. And then we're going to finish this workshop with the final remarks and the closure of the workshop. So I want to put some rules of the game because there are much more participants than I expected. There are 200 participants. For the moment, we are 100. So we need to put some rules to make some order. Otherwise, the things can become very chaotic. I didn't want to put a limit in this presentation, but I never also imagined that there will be so much participants. So first of all, I wanted to let you know that this workshop is being recorded. It's being recorded. So because we're a lot of people, I want to ask to everybody to have your cameras off and Microsoft off if you are not speaking. No, I would like, please don't speak during the presentation, also just for respect of the presenter. During the question sessions or a discussion session, please raise your hand for speaking. Don't unmute you to talk. And I will see who is want to. I will select the people. I will try to. We are a lot of people, so I will try to make everybody participate. I will make my best effort for this. If your microphone for some reason doesn't work, we have Tanaka Chatema here that will help you to please type your question to Tanaka, and Tanaka will tell you the question that you will have in your behalf. And then if you want to talk, for sure you have to unmute yourself. You can put your camera on. It's always very nice to see at least first time your face, the face of the person who's talking. You can do that if you want. And after the question, Tanaka is going to unmute you, mute you, and remove your camera. And as I told you, this is to save connection because we're a lot of people, so we have to make our best effort to respect these rules. Like this, we will save WinBeat internet connection. And we don't know, maybe some of you don't have so much very good connection. So at least this will allow us to have a workshop of quality. And if you have finally point, if you have any questions about the organization of the workshop or any technical difficulty, please write the message to Tanaka. Well, thanks a lot for joining this conference, and please enjoy it. I hope we'll try to make the most interesting possible, and we'll try to make the most dynamic, and we'll try to make in a way that you will learn and you will get something from this workshop. Thank you. So now we are going to, I don't know if Carl is, I give the word to Carl. Please, Carl, give us the opening remarks.
Hi, Santi. I'm hoping that folks can see me here, but I'm really happy to be here and to listening to this workshop. It's been a long time coming, Santi, and I'm glad to hear that you have a great audience out there for such a great set of work that you've done. The program itself really does cover a nice range of approaches to sanitation and drying and those things that we need to look at. I mean, if you think about it, the supermajority of the globe, it doesn't have sanitation, really. And I'm not going to say adequate or safe sanitation. I really don't like the term safe sanitation because sanitation is binary, right? You either have sanitation or you don't have sanitation. I mean, there's no such thing as close to sanitation. It is or it isn't. There's no Schrodinger cat of sanitation. And globally, there's also an increasing awareness that centralized processing of human waste is being stretched as there's an increased urbanization and existing sewer systems are inadequate. And this is profound in developing countries, but it's as problematic in countries such as, with advanced centralized processing, such as the US or Europe. So there's an ever increasing interest in decentralized sanitation. But in the effort to achieve decentralized sanitation, I don't know, for want of a better term, the rather unimaginative approach is the reduction of the footprint of centralized processing systems and trying to get them down to a smaller scale package plant that could be used in a neighborhood system or at a home. Perhaps a septic tank. That's very old and old style, but very traditional in a way. The form of this package plant concept, it's restricted by the type of components that have to go in there and trying to achieve that separation of the solids from the liquid in a way that presents things that aren't hazardous at the end. And the septic tank is definitely hindered by the fact that if it is not used as well as it should, or if it's overburdened, things like hydraulic retention times and shocking the system and perhaps not having the performance that you need can result in a lack of sanitation in a situation if we're not ready. But to achieve any further advancement in the types of sanitation that we want to see, we really have to look at the fundamental components of what's going on. And that is really where this work comes in. It's amazing to me that in these millennia, we've not understood more about the thermal drying coefficient of feces, because that ultimately drives the engineering thought process to how can we actually deal with this problem. This is not a problem of personal risk on human feces. This is a problem to be solved along the lines of, the mechanical and chemical processing of that feces. And when you look at the plants and the systems that we have nowadays for other things like fossil fuels and plastics and all of those things, we've even got biodegradable plastics now that are made from potato starch and cellulose and cassava byproducts. But we've never really put a lot of effort into understanding our own waste that we all sort of dispose of every single day in a way to be able to treat it better and turn it into a process that can be compacted and brought into the household in a white goods system, or it can be used at a neighborhood scale in a very effective way. And in all the time that I've been involved in this, and that's not as long as some of the people that are speaking today, one, and there's several, but one of the major problems has always been dewatering and drying. And we have to learn so much about the material that is human feces, right? It's been surprising me, it's fascinating stuff, to understand how that dewatering and drying process works, because it's expensive to move water around. It's expensive to burn off water from something to achieve that sterile form, or to be able to transport it in a cost-effective manner to another location to be processed. So I'm looking forward to hearing everything that's going to be discussed in this workshop. I'm looking forward to seeing the final results of the work that you've done and the related results that other people have done, with the hope that it's going to stimulate, that's a fundamental research that's going to stimulate greater ideas and better ways to actually improve how we deal with human waste in decentralized systems, and very particularly in ways that can be adopted quickly for developing countries. So thanks for inviting me. I'm looking forward to hearing all this. I'll be here today and tomorrow all the way through. And I hope that at the end of this, everybody is as satisfied and is sated with information as I am hoping to be as well. Thank you, Santi. Over.
Thank you, Carl. Thank you for inviting our invitation to give the opening remarks. Now we're going to have to Dr. Pillay, another fundamental piece on the sanitation world. He works for the Water Research Commission here in South Africa. Please, Sudhir, I give you the speech.
Thanks, Carl. Thanks, Santiago. Just going to go to the strategic importance of drying of human fecal waste. And this is coming from a WRC perspective, where we try to fund a lot of the new innovations around sanitation and water. Just a quick background, we're based in South Africa. We were a government entity and established in 1971. And our role is to focus on strategic issues and challenges. And we fund a lot of projects, including some at UKZN, where they're looking at some of the drying kinetics parts. The reason why this is important to us is that we've been learning through our development of new technologies and new sanitation technologies, whether they decentralize our household systems. The graph you see on the left and the biochar at the bottom, this was one of our very earlier projects in 2013. We could get the temperatures up. And so you had biochar getting made, but there were all different other aspects related to the actual equipment. So we found that the crust was forming inside the system. Once it crusted, it was difficult to actually remove. So the stickiness of poop was important. One of the things Santiago was doing at the same time, he was looking at optimization of the LADEPA machine that was developed through Tequeni, and it was a very innovative decentralized system. And so he was looking at the drying kinetics. And one of the most important things he pulled out from his research was actually, how does poop actually dry? Now, there's a lot of stuff for sewage sludge, but actual poop is quite different. And then there's a variety of poops just because there's different sanitation systems. And so we've been learning that we probably there's a big knowledge gap for different drying kinetics for different types of poop. We've been having some big pilot scale systems where we're trying to convert the waste into different heat treated products. And we found out there were big knowledge gaps, and how we can optimize this was very important. Chris will present after me. He always presents the Bristol stool chart. But basically, if you want to design off the grid, you need data. And there was a big knowledge gap. If you look on the left, there's different types of poop people make. And you have to design around that. So whether it's a wet, and Santiago was talking about wet poop. If you go to India and Indian countries where there's more washes, the water content is very important as part of the drying process if you want to move into thermal treatment systems. So we found that this is not so easy in the diversity of approaches that we want for off-grid. On the other side, we're looking at decentralized systems. So you're getting poop from different places. And it's quite different. Latrines, households, septic tanks, they're quite different. How you manage this diversity of incoming waste streams was very important. And there needed to be some type of pooling of knowledge. Now, from South African perspective, we focus more on normal human fecal waste as it comes out of the bum, basically, and VIP latrines. So nothing was focusing too much on wet type of latrines. The reason for this workshop, and I think it's a good important, if you look at the program, you have various geolocations of where research is coming from. It would be very nice if guys could put in a nice paper on this where you combine all these learnings together. I would, from my perspective, I would really appreciate something like that, and having a document like that. That would be really great for those people that want to design better and more efficient systems. Some of the results we've actually been using now as we're going through our development processes. So we've been using a lot of the results and the findings to design more efficient systems and products. We're finding that when we first started this journey of designing these new off-grid systems, the goal was first to get to a temperature where you can get a product. But now it's looking at more, how do we retain the heat? Insulation, those type of things. How do we put insulation materials within our own civil, like brick and mortar? So those are the types of options we are looking at the moment. So a lot of this underlying research and understanding how poop dries was very important and critical into how we design more efficient products. So I think Santiago will go into bigger detail than me. I just gave an overview of the strategic importance from our side and the strategic importance of having this type of workshop. As I said, I would love to have a paper that combines, the learning from Technocrat, the Cranfield data, the UK ZN data. I saw Tanzania also put in some stuff. I would love all of this in one type of document, easy to read, 12 pages, and just to have a general idea of what people need to look for. So thanks, Santiago, and it's over to you.
Thanks a lot, Sudhir, for the talk, for sharing with us your perspective. Now, I would like to finish the opening remarks is Chris Buckley, Professor Chris Buckley, who is head of the pollution research group at the University of KwaZulu-Natal, where actually I make my investigations on fecal sludge drying. So please, Chris, I'll let you this speech.
Good afternoon, everyone. It is a great pleasure to welcome you all to this workshop. And I'd like to just dwell a moment and congratulate Santiago for this program that he and his team have put together. It is difficult enough to organize an international workshop. It's even more of a challenge to do so during these trying times when we're trying to do it online and we've had very little experience previously in doing it. Great thanks to the Bill and Melinda Gates Foundation and the Water Research Commission for their support of these research activities and for allowing the expansion into some of the less obvious physical properties which are necessary to explore when gaining a deeper understanding of drying and the processing of fecal sludges. The speakers who have offered to contribute their knowledge and experience to the workshop, thank you very much. And I hope that your interaction with the audience will enhance your and expand your knowledge of the topic. The research students who've been involved in undertaking research into these topics with such unattractive sounding names as the water activity and viscosity of fresh human feces, or the stickiness of feces at different moisture contents. Without your enthusiastic involvement, this knowledge would not have been created and would have been in a far worse place without it. Thank you. We have to understand that the need for sanitation is very great in tropical and subtropical countries. And of course, what we do have there is adequate supplies of solar energy. So the coupling of the drying of fecal sludge or even the pasteurization with solar processes is obviously a step in the right direction, and it enables us to have a low external energy input system. And you, the audience, thank you for making the time to attend this workshop. Your interaction is crucial to the success of the event. So please try and interact as much as you can, and we'll explore whatever ways we can of enabling more interaction to take place both during and after the event. So I would like to think that we could reflect back on this workshop and think about the FSMX series of conferences, the FSM 1, 2, 3, 4, and now we're coming up to FSM 6. They too had a very modest beginning in Durban, and the original concept was supported and encouraged by the WRC, and they have grown into an internationally and professionally managed juggernaut, which is going to carry on and get bigger and bigger as time goes by. So I only say to you now, please enjoy this workshop, interact with people both on and offline, share your experiences and your wish for knowledge, and learn. And may you all have a very successful workshop. Thank you very much.
Thank you, Chris. Thank you for your nice words. So now I have to thanks again to Carl, Sudhir, and Chris for your very worthy words. Very appreciated and very motivating for the beginning of the workshop. Well, now this said, we're going to go to the first presentation of the day. This presentation is going to be given by Dr. Samuel Gerahun. Where is Sam? Are you there, Sam? Well, Sam, he works for us at the Pollution Research Group, University of KwaZulu-Natal. He made a postdoc with us. He was the principal researcher during the research project on Faecal Sludge drying, that from where this workshop is issued. So yes, during this presentation, he's just going to give an introduction to Faecal Sludge drying, because maybe there are some people that are very practitioner and not too much in the theory. So we're going to give a little of theory, and yes, and it's going to be Dr. Sam. Thank you, Sam.
Thank you, Santi. Thank you very much. Do you see my screen? I shared my screen.
Yes, we see it.
Okay. Okay. Thank you, Santi. In this presentation, I will try to cover some of the basics of Faecal Sludge drying. As Santi mentioned, I am a postdoc at Pollution Research Group. I have been part of this drying project with Santi. And I will try to cover as much as possible for people who are not familiar with drying concepts in general. I'll just give the background. To start with the definition, drying is defined as the removal of moisture from the moist solid, slurry, or liquid through evaporation. It's important to differentiate this term from the term dewatering. Sometimes they overlap and people mix up the two definitions, but dewatering usually refers to the removal of moisture in liquid form. So drying is a common chemical engineering unit operation widely applied in the industry, particularly in the food industry, to remove water to elongate the shelf life of perishables and to minimize pathogen activity. When we look at the drying phenomena involves heat, mass, momentum transfer, and phase change simultaneously. So the transfer of heat to raise the wet temperature and to evaporate the moisture content, and the transfer of mass in the form of internal moisture to the surface of the solid, and subsequently to evaporate the water in the material. So the main driving force for drying process to take place is concentration difference. The term we are using here is the water activity in the air and the water activity in the solid. Water activity is defined as the ratio of the vapor pressure of water in the material and the partial pressure of pure water at the same condition. So when the water activity in the air is less than that of the water activity in the solid, due to the concentration gradient, the moisture will be desorbed to the ambient air, and the reverse is true. That means adsorption takes place. When the water activity in the air is greater than the water activity in the solid. Well, whenever we have the equivalent amount of water activity in the air and water activity in the solid, then we'll have thermal equilibrium. And we need external forces to achieve drying process. Let's talk about the kinetic of drying process. Here we are looking at a drying curve, time versus moisture content. Drying has three basic drying rate periods. The first is called the constant rate period. In this period, the surface of the solid remain wet so that the free water is always available for evaporation, and heat and mass transfer takes place at the surface. And once the critical moisture content is reached, we then find ourselves in the first falling rate period. And this period, the drying period starts to decrease, and the surface water activity falls to less than 1. The first falling rate period occurs when the wet spot on the surface continuously diminish until the surface is dry. And the second falling rate period begins when the surface is completely dry. The heat required for moisture removal is transferred through the solid to the vaporization of the moisture in the solid, and the vapor moves through the solid into the airstream. So the amount of water removed in this period can be relatively small compared to that of the constant rates and the first falling period. So this is that was the basics about the drying kinetics. Now let's just talk a little about drying beds. Drying beds are one of the common infrastructures that are commonly used for the drying of sludge. They have their own advantage and disadvantage. They are obviously one of the lowest cost options. They require a small amount of operator and skilled manpower, low energy consumption. But on the other hand, they have their own disadvantage. They require more land than fully mechanized methods. They must be designed with careful concern for climatic effects, and they seem to perform poorly. And removal of of materials is usually labor intensive. Having said that, we have thermal drying methods. When we say thermal drying, there are different mechanisms like convective drying. We have conductions through hot surface contact. We have infrared drying, solar thermal drying, microwave drying. Thermal drying obviously performs better than all systems like drying beds, but is more energy intensive and requires more investment. In the drying sector, there are potential developments in technology recently, such as fry drying technology, which is the immersion of the sludge into hot oil at around 150 degrees centigrade, so that the oil penetrates the sludge particles and deliver the heat directly to the water inside. We also have steam drying. The steam drying principle as superheated steam that is blown onto the product, transfers the sensible heat to the product to be dried, and water will be evaporated. We also have the application of acoustic waves, mechanical vibration during drying. We have pre-treatment techniques such as ultrasonic and foam mat systems that aid the heat transfer process and facilitates drying operations. So when we say sludge is made up of unbound moisture, bound moisture, and dry bone solid. The water is bounded in different forms. We have unbound water, which is called free water. We have surface water on the surface of the particles. We have interstitial water that is trapped between the spaces in the particles. And we have intracellular and chemically bounded water. There is a good chance to remove the free water, surface water, and interstitial water using different dewatering, mechanical dewatering and natural dewatering mechanisms. But in order to remove the intracellular and chemically bound water, we need to apply thermal energy. Once all the water is removed, we'll be left with the dry bone solid, which could be hygroscopic or non-hygroscopic, depending on the physical-chemical properties of the material. So during drying process, the slurry or the sludge transfer goes through different steps: slurry to semi-solid and then to granular solid. And it goes as the physical changes involved in it, like shrinkage and change of consistency. And the second one, from semi-solid to granular phase, it involves sticky phase, formation of crust and cracks, and chemical modifications. As mentioned earlier, stickiness is widely observed in the sludge drying process, showing a great negative impact on the sludge drying efficiency. Stickiness is a phenomenon that reflects the tendency of some materials to agglomerate and adhere to contact surfaces. And this creates a problem for drying operation. Similarly, crust formation affects the evaporation of water from the internal part of the sludge. Just to mention some of the challenges that we face during the thermal drying process, we have high operating costs, high energy demand to evaporate the water. We have high capital costs. It requires skilled labor and expertise. High maintenance costs due to clogging and fouling and other negative impacts due to the process parameters. And we have lack of available data. This is critical because that's why we are here. In order to be able to implement or design a process that will enable us to dry fecal sludge efficiently, we need data. And that has been one of the bottlenecks of this process. Having said that, I will give the platform to Dr. Santiago to share his research outputs. Thank you. Over to you, Sam.
Thank you, Sam, for presenting and to give a nice background about what is Faecal sludge drying and to better understand it. So now it's time to go to what the research, so a summary of the investigation that have been conducted at the Pollution Research Group. We're going to call it PRG because it's easy like this. And then, so presentation, yes. Can you see it? Okay, well, so let's go on to talk about the investigation that have been conducted at the Pollution Research Group. Well, first of all, I will introduce what is the Pollution Research Group. It's located in South Africa, in the city of Durban, which was called the eThekwini municipality. Our research group, it's a research group affiliated to the university. We are a little independent from them. We are not really linked to the academic side, more research. We are affiliated to chemical engineering, and here in our laboratory we have, as we can see in the photos, we have a chemical laboratory. We have some prototypes. We have some instruments for physical analysis. We have for sure a place to work with whiteboards, with chairs, tables, etc. And also we can see a photo. If you can see a pedestal there, this is a pedestal from a reinvented toilet. It's a front end from a reinvented toilet. And we were, before taking it out of the field, we were testing in our laboratory. This said, what is the different research on drying? What we have quite a lot of master and PhD that have been funded by the Bill and Melinda Gates Foundation through the program Reinvented Toilet Challenge 2 and the engineering and field testing programs. And we have studied the convective drying, solar drying, rheology, stickiness, physiochemical properties, effect of aging. We also received all this a grant from Bill and Melinda Gates to expand our research on drying. And this is the project from where this workshop is related to. And the Water Research Commission also has funded us a lot of projects to study the infrared drying, to the LADEPA process, and also to conduct a lot of research of solar thermal drying. And we have a new project that's going to come. It's about the study the boundedness of moisture. So what is our feedstock in our investigation? Well, we work with real material, material that comes from on-site sanitation facilities. For the moment, we have used the fecal waste from the on-site sanitation facilities that are available in the municipality. So we have used fecal sludge from urine diversion dry toilets. With these toilets, we separate urine and feces, ventilated improved pit latrines. Basically, pit latrine a little with an improved structure, but where feces and urine are mixed, plus some waste and toilets. And also, we have studied like from anaerobic buffer reactors from a decentralized wastewater treatment systems, which are kind of big septic tanks. And we also have used fresh human feces that we have obtained by donations and with people from the university. And our laboratory equipment, we have different devices. We have experimental rigs to study infrared dryer, LADEPA. We have solar thermal dryers, convective dryers. We have thermobalance moisture analyzer, TGA. Thanks to this, we can measure the drying kinetics in head of reaction. We can measure the water activity. We can also have the setup of saturated salt solutions. We have a centrifuge, and thanks to this, we can measure the boundedness of moisture, the waterability, equilibrium moisture content. We also have some equipment for the mechanical properties, science detection analyzer, rheometer, penetrometer, and thanks to this, we can measure consistency, rheology, stiffness, among other mechanical properties. We have calorimeter, TCI, chemical analysis, different chemical analysis equipment. And thanks to this, we can determine the physiochemical properties of the sludge. We have oven and muffle furnaces, Ascaris deactivation setups. And thanks to this, we can make the drying and pasteurization performance. And also for the prototypes, we have other things to characterize the drying conditions, the more important things, which will be flow meters and nanometers to measure the air velocities at given locations, thermocouples, and hygrometers. And thanks to this, we can measure temperature, relative humidity, flow rates, velocities. So we also have worked in the field testing of technologies. The first one we can see is a solar dryer developed by Swansea University and currently is under testing in the municipality. The municipality under the platform of engineering field testing of the Bill and Melinda Gates Foundation. And so we are testing it before its commercialization and implementation at larger scale. And this is the LADEPA, which is the LADEPA is an infrared dryer. So the sludge is pelletized into pellets and then goes through infrared emitters. And then the sludge is pasteurized and dehydrated and can be reused. And so we also have work in testing this technology with the municipality. And also we work in developments, our own solar thermal dryer technologies. Here are some photos of small prototypes that have been developed with grants from the Water Research Commission. And here's some CFDs and conceptual designs with these works have been in collaboration with mechanical engineering and the energy of solar thermal energy research group at Stellenbosch University. So, so what's the investigation related to drying? What we have been done? So we have been studying the effect, characterize the material. So we characterize the rheological properties, thickness, sludge boundedness, physiochemical analysis, shrinkage. That's the thing we focus on the material. We also focus in the process. While focusing the process, we try to determine different important parameters as the kinetics, head consumptions, operating conditions, the equilibrium points, the efficiencies of the system, other analysis. And the dried product, we try to determine the physiochemical properties, pathogen content, if there is a cross, cracking, other kind of things that a consistency that can be useful for the reuse of the material. So here, summary of our results. So we have a lot of results and I will try to be fast. So sorry if there's too much more information, but then we can discuss of that later. So here we can see that, for example, drying kinetics, different drying kinetics of three types of fecal sludge, ABR, VIP, and UDT, and feces. Here we can see that there is a great effect of temperature until 150, that from 50 to 200, there is a big, when we increase the temperature, the drying time decreases a lot. But then we can notice that between 150 and 200 degrees, there is not so much difference. So we also can see that there is a big difference between the feces and the fecal sludge samples. And there's, especially at 50 degrees, we can see that, for example, for the fecal sludge samples, takes like from 60 minutes to 100 minutes approximately the drying, but for the feces, it takes like 120. It's almost a double from the ABR sample. However, if we go to the higher temperatures, it means above 100 degrees, we can see that everything dries approximately in less than 20 minutes. So we can see that we can see the effect of temperature when it's low temperatures. And something other results that are not here, but I would like to mention is that there is effect of size. So for sure, bigger it is, it will take much time to this is a trivial result, but we have observed it in the laboratory. The relative humidity has also an effect, especially at low temperature. Below 50 degrees, we noticed that the humid atmosphere, the samples dried less fast in humid atmosphere. But however, this effect of relative humidity disappeared at high temperatures. And then we can see the low effect of air velocity. Then if we talk about thermodynamics, well, this is, and here we can see some of the water activity versus moisture content. So the water activity gives an indication about the level of boundedness. When it's close to 1, we can see that the water is quite kind of unbounded, and when it's close to 0, it's very bounded to the structure. So here we can see how the moisture boundedness decreases as we remove the moisture content. So it becomes more and more bounded. But the first thing we have to see is that this at the beginning is quite stable, or the decrease is very smooth, very slow. But approximately around 20 to 30% of moisture content, there is a big drop in the water activity. That means that from this point, the moisture starts to be very, very bounded. And we can see with experiments that we couldn't see really a difference between the fecal sludge. Everything is in the difference under the uncertainties. So we cannot see really a significant difference between the materials. So and all this, we can also, something that we can see is that the water activity is never equal to 1. So that means that there is always a certain boundedness. And actually, we also measure the head of drying with our TGI-STA apparatus. And we could see that the head of drying basic is higher than the latent head of pure water evaporation, which shows that in a certain way, we require more energy to dry than evaporate water. And these values, there was a big uncertainty during the measurements, but basically it varies between 3,000 and 6,000 kilojoules per kilograms. And I've said the average was around 4,500 kilojoules per kilograms. Something that also I'm not showing here, I'm telling very fast, is that the material is hygroscopic. We make some tests also. You could see that the material can get moisturized after being in a humid atmosphere. And yes. So let's go to the mechanical properties. So here we can see the viscosity versus shear stress, and we can see here's some values were obtained in the what's called a texture analyzer, which is to measure the cohesive and adhesive force. So we can see when we decrease the moisture content, and basically we see the first graph in the viscosity versus shear stress. We can see that the viscosity tends to increase each time that we remove water. And so this increase of viscosity until a point where it's not anymore lost this fluid characteristic and becomes a solid. Then we can see that when we measure the cohesive and adhesive forces in our tensile analyzer, we could see that there is a peak around 50, depends on the sludge with the DLPUD, but it's between 50 and 60 degrees, the moisture peak with thickness. And during this peak is very, very sticky, the sludge, and will make the conveying more difficult. And something that we can see is that usually the sludge is much more cohesive than adhesive. That's according to our results. Talking about the physiochemical properties, just want to mention that we measure the nutrient content of carbon, the basic ones, the carbon, NPK, and some micronutrients, sulfur, magnesium, calcium, and sodium, also the calorific value, and could see that the drying don't affect these values in a dry basis for sure. However, if we see the results of thermal head capacity, thermal conductivity, we have the ammonium nitrates and nitrates, we can see that there is a decrease actually, even if in dry basis, there is a decrease when we dry. For the head capacity and thermal conductivity, when at raw moisture content, sorry, these results are with VIP sludge. But we can see that when it's very wet, the values of the head capacity and thermal conductivity is very similar to water, which could be expected because there's mainly water. And then when we dry, we could see how the decreases, and approximately until 40%, it decreases until 40%, and then from there it stabilizes again. And we can see that this is very similar for the ammonium nitrates and nitrates. And what's funny, like it's something interesting to see, is that the nitrogen content doesn't change. It's always constant. That's what we measure that. But it's formed as ammonium nitrates and nitrates, free ammonium nitrates and nitrates decreases. And I think probably because it gets linked also to the, in some way to the structure. That's something we have to explore. So if we remind our results from the previous slides, we can see that this decrease stops approximately when we're up to 30–40%, which is approximately the point where the water activity drops. So there's some relation between these results. And then if we go to pasteurization, the pasteurization, we studied it with Ascaris eggs. So in the first results, we put Ascaris eggs into Faecal Sludge and we dry at different temperatures. And here we can see the results, the first column of results. We can see the viability of these eggs. And we can see that approximately at 40 degrees Celsius, the viability doesn't change according to the different times. We can see also that this graph, in the X label, we can see the time. And there is no decrease of the viability with time. However, at 60 degrees and 80 degrees, there is a clear decrease of the viability of the Ascaris eggs with time. So 60 degrees is after 2 minutes, there is no more eggs, and at 80 degrees, it's very, very fast. And then less than 10 seconds, all the eggs are destroyed and they are not anymore viable. So we can see the drying by its temperature can destroy the pathogens, but only by this head input. And something that also we explored is we check the viability of eggs that were spiked into sludges, UD sludge and VIP sludge, and we let them, we dry this sludge at different moisture contents, and we let the sludge and the eggs to be there during a certain time. And then each week we were measuring the viability. If there was a decrease in the viability in moisture in a sludge sample dried at certain moisture content. So we studied until 20% moisture content. And we studied until 6 weeks. Actually, it was 12 weeks, but after the 6th week, we start to see fungi infection of the waste, and we have to discard it. But so what we can see is that the viability is reduced only below 40% of moisture contents after 3 to 5 weeks. That's what we can see. To wetter moisture contents, there is no effect. The viability was not affected. So we can see that also by removing water from the sludge, we decrease the viability of the pathogens, and for sure more water, there is less water in the environment, the viability is going to be lower. And something we cannot see here, but in the food industry, we usually relate the bacterial activation with the water activity. See here we can see that approximately the water activity, according to our previous slide, is inferior to 0.9 when we have 20–30% of moisture content. So that's, and according to those tables, this water activity is enough to deactivate a lot of macro bacteria, for example, E. coli, Salmonella. Okay, there is not too much time left, so I'm going to go very fast here in the morphological observation. So we can see cross formation, that there was a cross that was formed. This was bad because when there's a cross underneath the cross, the sludge can be wet. We also observe that was a shrinkage because volume reduction, formation of cracks, as you can see in some of the photos. The solid, we see that the sludge becomes granular solid around 40% of moisture content. We measure that the porosity of the sludge dry material was become more mesoporous. And we can see that there's a lot of loss of reflective surface, and we also measure it and change of color. Other considerations is the sludge degraded above 220 degrees Celsius. That's what we could see from TG experiments. And then we also could see that the sludge could be dewatered until 60–70% after centrifugation. We could not go up beyond 60% of centrifugation, even the more intensive conditions. And also we make some small emission analyses, and we detect that could be some volatile organic components. So let's go to the conclusions. So the sludge, there's a transition between a moist sludge to bone-dried solid. We could see that the sludge can be dewatered until 60–70% of moisture content. And the sludge look like a slurry or paste, and the water activity lies between 0.9 and 1. And most of the result of unbound water that could be removed by centrifugation or the watering, and could be potentially pathogenic development. And then we could see that between 60% to 40%, there is like this sticky semi-solid, which is and where probably some pathogen will be reduced. And then after that, we see below 30–40% of moisture content becomes solid. The sludge, the moisture content, the moisture starts to be very bounded to the solid, and probably this is going to destroy a lot of pathogens in this area because there is not the water activity start to decrease. And then we can see the transformation of the sludge going from until 40%. There is a big changes, all the time changes from changes in the consistency. And then we also see that the sludge is a mesoporous when it's granular, and it's hygroscopic. So it can, if it's very dry and he's in a humid atmosphere, he can gain moisture content. So we have to be careful during its storage. Then we also could see there's head energy demand, which is higher than the latent head of water evaporation, which is already high. And when we go to the solid, well, I didn't show the results, but we have some graphs that show that the energy exponentially increases. So we have to, from 30–40%, there's exponential increase of the energy demand, because the moisture that is remaining is very bounded. So we could see this important effect of temperature on drying and pathogen deactivation. But if you go too high, we can thermal degrade the sample. And also other things that we have to consider is the sample size, airflow rate, humidity. But there is, in type of fecal material, we didn't see there is really a trend. It's something that maybe we could think and maybe suggest from the results, maybe with the conclusion is maybe we should stop to 30%, something like moisture the drying, because otherwise after we become very slow, we require a lot of energy, very inefficient. So maybe we have to think what's going to be the reuse, but it could be a good moment to stop it. I would like to acknowledge to the Bill and Melinda Gates Foundation, to the Water Research Commission, and the Tiquini Municipality for all the financial support and also logistic support for the Tiquini Municipality. And also for sure for all the staff that there was a lot of staff and students and researchers, postdocs that were linked to these investigations. So, and also for sure all the background team, laboratory, workshop, administrative, with whom these projects cannot progress. Thank you very much. I think Yes, we are already out of maybe half. Sorry, I think I want to skip this session. We're a little in delay. I will answer your questions. So noted, please, careful your questions. We are going to, at the end of the discussions, where I want to answer your questions. But yes, we have already taken a little delay, so we wanted to go to the next speaker, who's going to be Patricia Labos from the MINSALB. Patricia Labos is a professor in MINSALB, it's an institution in France. Patricia Labos is an expert in separation process, especially drying. Currently, her research interests focus on the impact of sludge texture on flowability, particle engineering, via spray drying, and on the intensification of mechanical dewatering process. Dr. Labos also works as independent expert for the research executive agency of the European Commission, and he's going to be also presenting the work for Martial So, which is assistant professor at the same institution. His research is focused on the development of processes for solid design based on the use of supercritical fluids. In parallel, he has gained an expertise on the rheological characterization of pasty and granular materials, including sludges. And more recently, he has developed a thematic on 3D printing based on filament deposition for pharmaceutical and food applications. So welcome, Patricia and Martial. I give you the speech, and for the audience, sorry, I promise you I will answer your questions at the end. Please, Patricia, you can go.
Okay, thank you so much, Santiago. I will share my screen with the other participants. I think that now you can see my screen. Is it okay?
Yes, yes, it's okay.
Okay, so thank you very much, Santiago. Thank you for inviting us to participate to this workshop. Brief introduction, I have been working on the issue of sewage sludge drying for over 25 years now. And the prime focus of our activity here at IMT MINALB is what professionals call contact or indirect dryer, and particularly paddle dryer. So during this presentation, I will try to share with you some developments, recent development we have done on modeling this drying in paddle dryers. I will start with a brief introduction about the technology. The common features of all the indirect paddle dryers, of all indirect dryers, sorry, are the fact that the heat is transferred to the sludge through a heated surface over which a product is transported. The heat is provided by thermal oil or steam that is used as heating fluid. And most of the time, the drying process takes place in an atmosphere that contains only the liquid vapor. That means that the mechanisms involved during the drying process is very different from what we can see in convective drying. That means that most of the time in indirect dryer, heat transfer is rate limiting. We don't have any mass transfer resistance. But sometimes people use air or inert gas as sweeping gas, and then we have again air inside the dryer, and we have also to take into account the mass transfer limitation. The main advantages of contact dryer is the compactness and is the low exhaust volume, because we don't have air inside the dryer and we have only to treat the liquid vapor that is released during the drying process. But the main problem is connected to sludge stickiness, to clogging effect, and also to the fact that it's difficult to control the process and to adjust the final total solid content of the sludge at the dryer exits. That means that most of the time, the total solid content is very high and is sometimes higher than 95%. You have here some pictures showing different technologies So when we talk about contact dryers or indirect dryers, that means that we talk about disc dryer, paddle dryers, and thin film dryers. If you want a description of this technology, you can find some information in the book chapter we wrote some years ago with Professor Angélique Léonard from Liège University. Now, looking at context in Europe, we have two main disposal routes for sewage sludge. We have agricultural valorization or waste to energy conversion. The typical sludge composition is given here. If you look at the ultimate analysis, you can see that the volatile matter in municipal sewage sludge is quite high. That means that these sludge can be turned into an interesting material for energy recovery. For that, we have different techniques. We can use dedicated incineration, co-incineration with municipal solid waste, or gasification. And the optimal moisture content required for these different processes is much higher than the moisture content that could be reached with pure mechanical dewatering. That means that partial or full drying is compulsory if you want to turn sludge into energy. But of course, as I said previously, the drying content at the end, at the exit of the dryer is very high, much higher than the threshold provided here. That means that we have also to optimize the energy consumption on the whole processing chain and to avoid over drying of the sludge. So we arrived to the conclusion that we need a predictive tool for process control. We have a lack of knowledge on fundamental mechanisms for disc and paddle dryers modeling. However, reliable information have already been disseminated in the scientific literature. For instance, looking at the heat transfer, we know now that the so-called penetration theory is widely accepted, even if there is a lack of consensus on the choice of the characteristic dimension that should be used for describing the behavior of the piping bed. For sludge flow, we have a consensus on the range of moisture content where we can observe the sticky consistency. We know that the peak is around 55%. That corresponds exactly to the value given previously by Santiago. We have a granulation around 45%. But the main problem is that the viscosity of the material is unknown for very concentrated states, and computational fluid dynamics is out of reach. So we decided to select a stochastic approach based on Markov chains and the so-called penetration theory to establish a model able to describe the drying process in disc and paddle dryers, and also able to be used for process optimization. So I will just summarize the fundamentals of this model. Everything has been published in the literature and is fully available. For investigating the drying process, we have designed a homemade lab-scale paddle dryer. You can see the dryer here. It's a U-shaped jacket throw with a rotating shaft on which are screw paddles. You can see here the design of the paddle. The sludge is fed on one side, flow inside the dryer is heated and is discharged on the opposite side, while when the water is extracted here. So you have here a schematic representation of the process. We have several process parameters that could be changed during the exposure experiment. We can control the flow rate, the steering speed, the slope, and also we can adjust here the discharge level. This has an influence on the amount of material that is retained inside of the dryer. For the assumption, so we consider that here in gaseous atmosphere here, we have only vapor. That means that we consider drying by boiling, so no mass transfer resistance. We have a constant wall temperature because here everything is heated by electrical resistances. And we consider that the sludge could be modeled as a component containing only total solid and water. We didn't take into account the fact that ammonia or something else could be released or is released during the drying process. And we also assume that we have a constant holdup here along the dryer. This assumption is probably the most questionable. And before developing this model, we have performed design of experiments, for instance, to establish empirical correlation that could give the holdup as a function of the slope and of the discharge level. So, first part of the model concerns the way we describe sludge flow inside the dryer. So here you have a photo of the shaft with the paddle. So when you use a Markov chain, you have to decompose the volume into a series of small volume. And here we decided to select a small volume around the paddle. And we model the process as a series of continuous stir tank reactors. In fact, we have 18 because it's the number of paddle we have in our lab scale dryer. And we consider that inside this volume, the temperature and the composition is homogeneous. Once the sludge is here, so the sludge has a given probability to remain in this volume, but has also a given probability to move forward or to move backward. So using Markov chain, we can compute the transition probabilities between two periods of time. So here are the expression of these transition probabilities, and we can build the matrix of transition probability. This matrix then is used to compute the evolution of the state vector, knowing the state at the time t, and knowing the filling conditions. So with this model, we are able to describe the flow inside the dryer. So now we need to have a model to describe the heat and mass transfer. So for that, we use the so-called penetration theory developed by Schrunder some years ago. The continuous mixing process in this theory is described as unsteady mixing step. So we have a period where the bed remains static and heat is transferred from the wall to the bulk. We have two in-series resistance, one corresponding to the contact here, and the second one corresponding to the heat transfer inside the bed. And at the end of this static period, we have an instantaneous macro mixing here, and the temperature and the composition are again homogeneous, and we move again to a static period. So this penetration theory describes a sequence of unsteady mixing steps. So this model is able to, can be used to compute the amount of water evaporated and to compute the temperature evolution as a function of time. When we developed this model, we have met an unexpected scientific difficulty, but which was specific to our homemade dryer, because most of the time in industrial dryers, the dryer is filled with maximum capacity. That means that the heated surface is equal to the exchange surface. But in our dryer, as you can see here, when the drying process occurs, part of the heated surface is not in contact with the sludge. That means that the heat is not used for drying. So we had to introduce something to describe, to compute, to estimate, in fact, the contact area. So I will show you a quick glance at the results. So you can see here the evolution of the moisture content along the dryer and the evolution of the temperature. As you can see, we are using a drying by boiling. We are describing a drying by boiling models, and the experimental results fit quite well the prediction of the model. If we look at the influence of the residence time, again, there is quite good agreement between experimentation and modelization. And on this slide, again, on the bottom part, we have a very high solid holdup. That means that, in fact, all the metallic surface are in contact with sludge. So we are able to predict quite well the drying kinetics. But when the solid holdup is low, in fact, the assumption that all the metallic surface provide the energy to the sludge is not true. And we have to introduce a variable area to compute, to estimate, in fact, the heat exchange surface to be able to describe adequately the drying kinetics. So we have a homemade lab scale continuous dryer that is available for experiments. We have developed a stochastic model that is more or less validated at the lab scale using different approach for describing the exchange surface. This tool is available for process optimization, but we think that we can do something more. And you can see here the evolution of the sludge inside the dryer. We have a pasty material, we have the stickiness phase here, and the granular material at the end of the dryer. And we have the intuition, in fact, that the recirculation coefficient that for the moment is taken constant along the dryer. We have the intuition that this coefficient is a function of the total solid content. And we want to introduce a correlation between rheology and solid content and, of course, probability. That's the reason why our ongoing work concerns rheometry. We have investigated the behavior of pasty material using conventional rheometry, but we also use commercial shear testers that are widely available for powder characterization because people that use shear testing have established classification of powder probability based on an indicator that is flow function index. So recently we investigated, we compare both approach, and you can see here that results match quite well. And this confirmed that this approach confirmed that the sludge is very, very, very cohesive when the total solid content range from 23 to 43%, which confirmed the results obtained by Santiago team recently. So thank you very much for your attention. If you want to contact us, feel free to do that. And if you have questions, I can answer, of course.
Thank you, Patricia, a lot for your presentation. So we're going to have for just 2 questions. If somebody from the audience has 2 questions, raise the hands. Well, I think don't see. I don't see any questions, I think. Please, just let me know by raising the hand. I will read. I'm not in this moment reading cannot read the chat in this moment, but let me see in the chat. Okay, yeah. Okay, there is a question. Yes, there is a question here. The Sagra Netrai Patil. I suppose that is directed to Patricia. What is the capacity and power consumption of the dryer?
Okay, so for our lab scale dryer, the capacity is around 10 kilograms per hour. And for the power consumption, I don't think that the information is reliable because, as you have seen, due to sludge shrink rate during drying, part of the energy is directly supplied to the atmosphere and not used for drying. I will try to find the information regarding industrial paddle dryer, and I will provide the information in the chat. I think this information concerning the industrial dryer will be most reliable than the one we have at the lab scale.
Thank you, Patricia. Thanks. I don't see any more questions. Thanks a lot. Anyway, if somebody want to pose a question, we can do it also in the later stage. Thanks a lot for having accepted our invitation to the workshop. Now let's go into with Professor Angelique Leonard. Professor Angelique Leonard is a chemical engineer. She obtained a degree in 1998 from the University of Liège. Now she's professor within the Department of Chemical Engineering at the University of Liège in Belgium. She obtained the Frederick Schwartz Prize for the Division of Science of the Royal Academy of Belgium, among other merits. She organized in 2008 the first edition of the European Conference of Sludge Management at the University of Liège. From January 2016, she's the chairperson of the European Federation of Chemical Engineering, working party on drying. In this capacity, she chaired the organizing committee of the 6th Euro Drying Conference, who also was in Liège. Her research interests are convective drying of deformable porous material, including sludge treatment as the water when drying, X-ray microtomography as a tool to characterize the texture of porous material. And she also is looking at life cycle assessment. Okay, thank you, Angelique. And yeah, I give you them. Please go ahead.
Okay, can you hear me? It's okay?
I can hear you and I can see your presentation.
Okay, perfect. So thank you, Santiago, for this kind invitation. I must admit that it's a unique, let's say, opportunity for me to share the work with people coming from your countries, but also from Africa in general or other countries, because for, let's say, familial constraint, it would have been really difficult for me to join a real meeting. So it's a real chance for me to have this opportunity to share a part of the, let's say, knowledge that we have in the field of sludge drying. So with Patricia Labos, of course, we know her, we know each other very well since for many years, so more than 20 years in common, let's say, on drying topics. But in my group, we are more focused on convective drying, which is quite, let's say, complementary to what Patricia just presented. And so I have to say that, let's say, from my PhD thesis, I worked on sludge, so for more, let's say, than 20 years, so sludge drying. And let's say the original methodology that we developed in my group was the use of imaging technique, so X-ray tomography, to follow cracks shrinkage, as you mentioned in previous presentation, that can have some impact on drying quality, not necessarily for sludge, but understanding cracking phenomenon, shrinkage phenomenon can also be very important in link, let's say, with drying efficiency or, let's say, drying operation. So I worked, as you said, on drying and sludge. Then, let's say, lately, I also developed activities in life cycle assessments, and finally to couple different approach, because we are also active in projects about, I did not mention it in my presentation, but recovery of phosphorus and sludge, which is an issue in Europe in order to try to be more independent on the phosphorus resources. And so a lot of projects today are focused on the phosphorus recovery in either wastewater or in sludges. So first, why drying? But we had a very nice and complete introduction about sludge drying, about let's say kinetics and so on. So I will be very short, just on the let's say motivation for drying. Of course, if you think, as Patricia mentioned, the two let's say main variation ways in European context. You can either put the sludge on the land, so make land spreading to recover, I said, the nutrient values and so on. And if you dry it before, of course, you can have a stabilized product. You will reduce mass and volume for transportation. The nutrients will be concentrated. The product, depending on the temperature and the residence time, can be, let's say, hygienized. And also the texture, let's say, is more friendly because you go from, let's say, a paste to solid or to pellets. If you think to incineration, of course, if you try to burn a wet sludge, it's not very easy and it's not very interesting from, let's say, a heat value point of view. So it's, let's say, very interesting to reach a certain level of dryness in order to have, let's say, this facility to dry the product. And depending on the, let's say, final issue, so common incineration, or if you want to go for co-incineration or even pyrolysis or gasification, even if these two ways, let's say, are more still under development, you also need to dry the product. So about drying, it was already said, so I will be very fast. So thermal drying is a widely used separation process, which of course consumes a lot of energy. Figures, let's say, tells between 10 or 15% of the European industrial total energy use. And of course, we need to optimize the process, but also to understand the behavior of the materials. And everyone who has ever worked with sludge knows that from, let's say, one plant to another plant, or one place to another place, the sludge will behave or can behave totally in a different way. And so more in relation with the final quality, it's important to be able to follow several characteristics, as I already mentioned, such as shrinkage, cracks, or moisture profiles. And for that, so in my group, we use a microthermography. So regarding convective drying, so just, let's say, sending, let's say, hot air with a certain level of humidity on the product, we studied different types of materials. Initially, wastewater sludges, but the methodology was also applied to the type of product and typically soils also in relation with agricultural practices, but also to geotechnical materials, food materials. So of course, this can be adapted to lots of different materials. And in the group, we have both, let's say, an experimental and modeling approach. So for the experimental part, very quickly, so we have access to different dryers. So you can see here a view inside our lab that we called Hall of Chemical Engineering. So this is a superheated steam drying, which is equipped with two cells, one able to receive, let's say, about 1 kilogram of wet product, and a very small one just here horizontally placed, which is, let's say, designed to receive some, let's say, grams of product, so at a very small scale, so we can operate with two different, let's say, quantities of experiment. We have also a micro dryer purely dedicated to very small samples. So you can see just here a very small, let's say, a spaghetti or extrude of sludge after drying. And so we put it, let's say, under a balance. And in this channel, you will have an air with controlled humidity, temperature, and velocity. And with the balance, you can control the evolution of the mass. And let's say afterwards, you can, of course, compute the drying kinetics and so on. As I said, we have also microthermograph, so in order to visualize the external surface and also the cracks developing into the samples. Also at a large scale, so here you can see a picture of a fixed bed of sludge, so you can recognize the small spaghettis. We made some cuts in it. This system was used to study the impact, for example, of a back mixing operation. So if you recirculate dried sludge in a pastiche sludge, you can, let's say, enhance the drying because you will have a bed with, let's say, a higher permeability. So it's better for drying efficiency. And as we want, and it's also one of the, let's say, characteristics of the group to control what is the history of sludge. We have also some equipment linked with dewatering, so for example, a belt filter or decanter centrifuge, in order to generate ourselves in the lab under controlled conditions the dewatering sludge before making the drying experiments. So regarding drying technologies, there are different dryer types, as it was already mentioned. And so in our group, we are so mainly focused on convective dryers. So some, let's say, examples, so belt dryer, direct drum dryer, flash dryer. This table also comes from the chapter that Patricia mentioned about modern drying, and this chapter dedicated to sludge drying. So if you want, we can give you a copy of the chapter, and so you have different, let's say, characteristics regarding different technologies of drying. So the specific drying rate, the specific energy consumption for different types of technology. Some, let's say, practical realization. So you can see here a convective dryer, a belt dryer, which is installed in a small city in Belgium. You can see the preparation of the sludge on the belt, which circulates in the system with air crossing through the belt. Another realization, which is a low temperature dryer designed by the Bioconfigure company, which is also a belt dryer, but which operates at a lower temperature. So I decided not to show you equations or, let's say, a complicated approach, but to focus on practical, let's say, issues or difficulties that we can have when we dry sludges. In this, let's say, mind to exchange knowledge, because we had the opportunity to sludge, let's say, to dry quite an important number of different sludges. And what we can really say is that sludge is a complex material. Complex from a rheological point of view, but also complex, let's say, from an historical point of view. Of course, as you know, and it's more, let's say, critical for contact drying, if you have this sticky phase or glue phase, it can be very complicated. In some cases, you can break some part of the dryer and so on. And the way of the history of sludge can have also an impact on the way that this rheology will evolve with CCT. And concerning so the history of the sludge, depending, for example, of the chemical that will be used to make the flocculation of sludge, depending on the treatment conditions. So is there a digestion or not? So what is the dewatering technique? Is it a centrifuge? Is it a belt filter? Is it a press filter? All these operations will have an impact on the drying behavior. Also pumping conditions, if you store the sludge. So very, very, let's say, important effect on all, let's say, the treatment chain. So you can see here some, or the main, let's say, points that can have an impact on sludge drying. So origin, rheological properties, composition, the treatment underwent before within the wastewater treatment plant, and so on. And as you know, there are few really specialized manufacturers. Usually what they do is to adapt existing technologies, mainly coming from food industry. But in some cases, there are, let's say, errors that are made. And in some cases, some dryers are not operated in a good way at all. So it's important to diffuse good practices. So I will go fast on some example, practical example at the end of this presentation. So some results, as I said. Just here a picture showing you the influence of sludge origin. So it's a graph representing the drying flux, so kilogram per square meter per second, versus water content. So it's a usual way to present drying kinetics. And here you can just see that depending on 5 different locations, but near my university where the sludge were collected, the difference are quite high because you can have a ratio up to 3:1 in the drying rate that are observed. So that means a longer residence time and so on. If you look to a simple pumping operation, so in a wastewater treatment plant, we, let's say, collected raw sludge here, let's say, before a pumping operation. And we have just the same here with the plain blue dots, just after passing in a pump. And you can see that just with this pumping operation, you deteriorate completely, you destroy, let's say, the drying behavior. If you see the drying rate that was here close to yes, between 15 and 20, it goes down to 5. So you can see really that this pumping operation completely destroy, let's say, the drying behavior. You can, let's say, repair it a little bit. So if you add some lime that can help for conditioning, for example, you can, let's say, a little bit counterbalance this effect of pumping. And so if you see the specific evaporation capacity, you will divide it roughly by 2 just due to this pumping operation. So now if I go to another type of example, the effect of liming. So when you add lime to sludge, you can do it, let's say, before dewatering. This is the pre-liming, or after dewatering, and we have to mix the sludge to do that. So it's a post-liming. And in that case, you can see that if you see the, let's say, the raw sludge, or with pre-liming or post-liming, you will, let's say, enhance the drying behavior when you dry them in fixed bed, because you will have, let's say, a bed with a higher permeability. But it's better to make pre-liming than making post-liming. Another example is the influence of mixing. Let's imagine it's just like pumping. If you have to mix your products, if you compare, here we had also lime in the case of post-liming. So if we have first, let's say, the initial sludge here in a kind of between blue and green, you have a drying time of 73 minutes. If you add some lime, you will really, let's say, you will of course decrease the water content, but also you will decrease the drying time. But if you just mix the sludge, so before adding any lime, you can see that you will also increase the drying time and decrease the drying rate. So anytime that you mix, that you pump your product, it's quite, let's say, a negative for the sludge drying. But on the contrary, if you have a soft sludge, which is very pasty, sticky, one way to, let's say, to improve the behavior is to add a solid. So you can add either dried sludge, so we call it back mixing, or we also make some studies where we add sawdust. So finally, a wood product, fine wood particles. And you can see that if you compare the original sludge here in blue, and if you add, let's say, higher quantities of either sawdust or, let's say, a dried sludge, you will, let's say, improve the behavior of this sludge that was initially, let's say, difficult to dry. So you will reduce the drying time when you add this sawdust. And the, let's say, the advantage if you use a sawdust or any, let's say, other biomass is that you can also contribute to make a new biofuel, or to valorize 2 types of waste. Another type of example is the influence of storage. So it's not so good, let's say, to store during a long day or during long days sludge, because you can see that if you compare the sludge at day 0 when it's collected from the wastewater treatment plant, and if you let it at ambient temperature during, let's say, 20 days, due to some, let's say, evolution or re-fermentation in the sludge, you will completely, let's say, decrease the drying behavior, and the drying time will increase quite a lot. So just to end, of course, thermal, let's say, thermal drying is, let's say, a quite costing operation. And if you look to the distribution of the price when during drying operation, of course, the energy is the major contribution. So we have to try to decrease this consumption of energy. And it's even more important in Europe if we don't have access to a sun energy, or to, let's say, a solar, which is very, let's say, bright. So some ideas to reduce this energy consumption. Of course, it's better if you have a higher, let's say, CCT at the increase of the dryer. So if you try to optimize the dewatering step before, but it's not always the case or so easy, because in some situation, if you go, let's say, too high in the CCT after dewatering, if the sludge, let's say, it's too hard, it's difficult afterwards to make some spaghettis or extrudates, and in that, let's say, situation, it's quite difficult to dry the product. You have also to, of course, work on the design of the dryer. You can also try to valorize some heat present on the site. So it's quite common in Europe to try to use biogas coming from a biodigestion, using in let's say, heat and power system to recover, let's say, heat from this biogas. Or eventually you can also recover waste heat from incineration. And what is very, very important is to take into account sludge history. So I hope that you've understood that depending on the treatment that the sludge followed in the wastewater treatment plant, even a single pumping operation, it can completely change the drying behavior. And in some cases, your dryer is just not efficient because the sludge is not adapted to it. So to conclude, what is the future of sludge drying? We can imagine that tomorrow there will be the development of sludge drying with, let's say, within a zero energy wastewater treatment plant. If we try to integrate all, let's say, these different operations, and it's very important to have a vision of the whole site. If we think to, let's say, collective treatment of water as we do in Europe, and to try to reach so an hydraulic optimum. Of course, there are a lot of emerging drying technologies. It was mentioned using superheated steam or using, let's say, frying, so with, let's say, hot oil. But there are still research efforts that have to be, let's say, done to better understand the links between the sludge, nature, history, and drying. Of course, we make some observation about, let's say, the impact of this operation. But the idea would be to understand why, and this is, let's say, a topic in which we are still involved with one new PhD thesis just beginning yesterday on that topic. You can also imagine to try to use a heat pump or low temperature drying, and also it's another topic completely. But if you have different type of dried sludge obtained with different dryers, you can have different type of textures. A participant talk about the porosity of the sludge, and depending on that, let's say the efficiencies, for example, of a reactor making gasification or pyrolysis can be very, very different. So this is not complete, but some, let's say, ideas for further research. So I thank you for your attention, and if you want to have more details on this research, practically all the papers and PowerPoint presentation and so on are available on an open repository on the University of Liège. So if you click on that line, you will directly go on my list of publications. So that's it.
Thank you very much, Angelique, for a nice presentation. I don't know if somebody has a question. Oh, wait a second. Somebody, I don't know, raise the hand. Somebody wants to talk. Or in the chat, somebody has a question, a comment, or... Okay, so if nobody has a comment question, we are going to go to the next presentation. And the next now, thanks to again to Angelique and Patricia. There's one question in the chat.
Yes, I see a question about links between LCA and drying methods. Yes, 2 years ago or 3 years ago, I made a presentation about how to use LCA in the context of drying during, let's say, last IDS conferences in Spain. So if you are interested, I can share the presentation. You can find it on the OPI website at the level of university.
Perfect. There is another question from Blevi, which says, on the influence of mixing to speed up the drying, did you also try using the rice husk or any idea?
Yes, perhaps it could be a nice, let's say, suggestion for a collaboration, but as we are not producers of rice in Belgium, so we have access to wood waste, but not to rice. So if you have an idea of sending us some sample, we could try. That could be an idea.
There is another last question I'm going to take. It's from Samuel Gerahun. What conditioning mechanism do you use to alleviate the impact of stickiness during the sludge drying process? Okay,
as I said, stickiness is more a concern for contact drying. For convective drying, it's not really an issue because the product is not, let's say, agitated or let's say doesn't move during the process. But in some work done by some colleagues from the KU Leuven, they showed that if you use some specific coagulants, typically PAX, so it's a polyaluminium chloride, it was proved to have a positive impact of stickiness. In some cases, they show that the stickiness character completely disappears with the use of packs. So we tried also to use packs in the context of convective drying, and we also saw an improvement of the drying behavior. And I had a PhD student working on that topic, so he completed his PhD thesis some years ago. And so we use this, let's say, coagulant to make the test. So if you are interested, there are also some publication and even a full PhD thesis on the topic.
Thank you very much, Angelique. Well, thanks again to Patricia and Angelique for presentation and to share with your experience in sewage sludge drying, which I think we can learn a lot from there. But now let's going to go to Faecal Sludge, and this is going to go to South Africa, to the Tikwini municipality, Durban, where Sabelo Matengwenja, he's going, he's an engineer at the municipality. He deals with wastewater treatment projects and sludge and management. And so he's going to share his presentation about how the local municipality in Durban actually manage this fecal waste. Please welcome Sabelo, and we are listening to you.
Hi, good afternoon, everyone. I'll present today on this wastewater sludge drying using solar energy. Basically, this will be an experience sharing today. It's not that technical because we had some limitations on analyzing and fitting the kinetics into the curves. So basically, I had an idea of taking this project further, but there were those limitations, of which I hope in collaboration with PRG, I can take this project forward to analyze the wastewater sludge, waste activated sludge, and also raw sludge, the drying kinetics. Okay. Basically, my presentation will cover the project motivation, some sort of literature review, of which I think Dr. Samuel covered a lot of it. So I'll just fly through the literature review. Methodology that I used during my analysis, during my testing on site, and then some results and discussion, conclusions, and lastly, future work that was planned for this project. Basically, on the project motivation, eThekwini municipality is faced with a number of challenges, and in sludge management is one of the problems that we are facing in our treatment works. Currently, we spend a lot of money in transporting wet sludge. Our best case of the sludge that we're transporting, it's 25% total solids. The rest is water. So that means we're spending a lot of money in transporting mostly water as opposed to solids, dry solids. And in our work, in our plants, basically we're running 27 wastewater treatment plants, and most of the plants have conventional drying beds, at which most of them are not in use in full capacity due to long drying times associated with this type of technology. So basically, while on the other end, we have abundant solar energy that we can utilize to dry our sludge, which is free. And it has some added benefits like sludge pasteurization and also some potential to recover some of the nutrients. So I thought that was a good idea to explore this, and just, this is basically a pre-feasibility study to prove the concept that solar drying beds will perform better than the conventional drying beds. That was the biggest motivation. If I can bump up the solid contents and remove some of the water, and I'll save a lot of money for the council in transportation. Basically, this is a map that shows how can you convert the solar energy. You can convert it to electricity, chemical energy, thermal energy, of which we're gonna focus more on, and mechanical energy. And this map shows the South African, shows how much energy do we receive, solar energy that we're receiving in different provinces. Basically, Durban is not that great as compared to other provinces in South Africa. However, we still have decent energy. About literature sites that we were receiving about 1,550 kilowatt hour per square meter to 1,750 kilowatt hour per square meter, which is a decent energy that will help us. And the most important thing, it's a free energy that we can use. So that's why it has so much value. In literature, Dr. Samuel covered this. I'm not gonna discuss it again. This is a drying curve, which have 3 phases. So I'm not gonna go through this because we have seen it already. And this is the rate at which water is lost during drying process. The factors that are affecting drying, basically it's temperature, heating source, which is heating source, moisture, and the condition influencing the transfer rates. And there are external conditions such as air, velocity, and humidity, which is a very big limiting factor in Durban. We are having high humidity in our city. Okay, some of this has been covered by previous speakers as well, but just to go over it again, the type of drying, it's convective contact drying, convective contact radiative drying, convective and radiative, and lastly solar drying that we are going to focus on. The methodology that I used in this project, basically, I selected one site that had drying beds, open drying beds, conventional drying beds. So that site was Kingsborough Wastewater Treatment Works, at which I fed the waste activated sludge. So I did not use the digested or raw sludge. It was waste activated sludge. And then on my control, it was the conventional drying beds. And the test was the solar drying beds under the greenhouse. Basically, that's what we're doing. And the parameters that I monitors, earlier on in my presentation, I highlighted that we are limited on the instruments that we can use to analyze some of the parameters. So I just used the basic available parameters that I could monitor at that time, but which will give me a good indication on the effectivity of solar drying. This was the loading diagram. Basically, we had different grades of sand. Started with the coarse material, and then we filled with different grades of sand, and it was filtering out the water, and we have a sludge layer on top. I'll show you in the next slide. Okay, basically, this was my small drying bed. This is how I created my drying bed. And this is when it was filled with sand and sludge. So it was drying quite nice, and it mimicked the actual drying beds. So I took one of these containers into this greenhouse, which had higher temperatures, and the other one I took it outside outside the area so that it represents the conventional drying beds. I'm running out of time now. Okay. Okay, these are the results. Basically, you can clearly see from this slide, we filled with waste activated sludge into this. So on day one, on the sludge that was left outside to mimic the drying beds, conventional drying beds, on day one, we had some rain. You can see at the sludge that there was rain taking place. And after 14 days, you can see on my right, if I can show you, you can see on my right that the sludge is well dried. Okay, basically these are the temperature profiles that we're monitoring. The ambient temperature, which will be more associated with the conventional drying beds. You can see that the greenhouse temperatures were always higher than the conventional drying beds. So this reading was taken in the morning, and this graph shows the readings in the afternoon. In the morning, we saw a maximum of about 30 degrees. In the afternoon, we saw a maximum of 38 degrees Celsius, which also shows, which was in correlation with the previous slide, that the greenhouse temperatures were always higher than the ambient temperatures. Okay, now on total solids, I didn't present it using the moisture content, but if you can say 1 minus whatever total solid value is there, then it will give you the moisture content, and you can see it will follow the same profile as the drying curve that I presented earlier on. So on day 1, we had about less than 1% total solids in our sludge, and after 2 weeks, the sludge, the total solid went up to 89%, of which it's a very good achievement. And under controlled conditions, this can give us a lot of information in terms of the drying kinetics and whatnot. And that's where I want to go to with this. Okay, on conclusions, because we're running out of time, on the first day, on the day 1, we experienced a rain during the testing period, about 5 millimeters. The greenhouse temperatures were always higher than the ambient temperatures, of which means there's more energy that could be transferred to the sludge, hence more drying rates, higher drying rates at the greenhouse drying beds. Drying rates of the solar drying bed was always higher than the conventional drying beds. The greenhouse provided a protection against rehydration of sludge. I think that's a very important point, because what we see now in our drying beds, you find that you are ready now to remove your sludge, and 2 days before you remove sludge, you experience a rain, and then you have a problem. You have to wait another 3 to 4 weeks before your sludge is dried. Wherever, if it's in the drying bed, I mean, if it's in a greenhouse, you'll have that protection that it's not gonna rehydrate. Okay, future work that I would like to do in collaboration with PRG is to conduct a pilot scale study under controlled conditions and do most of the critical monitoring parameters and analysis, and investigate the effect of air preheating via solar heater, and fit the drying rates into the drying curve. And lastly, I think it's important that we consider the gas treatment or the exhaust gases treatment, because that puts a lot of environmental and complaints from the surrounding communities. So the treatment of the exhaust gases, it must be considered in our studies that we're doing. Okay, thanks a lot, guys, for your attention. Appreciate it.
Thanks, Abello. Thanks a lot for your presentation, and to see a clear example of the potential of solar energy, and especially in countries like South Africa or other countries in Africa or Asia, with the solar resource is abundant and can lead to decrease of the operating cost in drying. I don't know if there's questions around here. Somebody, nobody raising their hands. There is a question from SNG, and is the drying time lower with the drying solar method?
I beg your pardon?
Yes, the question is the drying time lower with the drying solar method?
The drying time, yes, it is it is lower. It takes quite. If you compare the two, just stop. If you compare the two, the one on the that was the conventional one, and the one which was in the greenhouse, you'd see that the greenhouse one had higher total solids, which implies that it dries faster as compared to the one at the conventional. And also, if you look at the temperatures, you'd see that the heat that will be supplied to that sludge under the greenhouse is more, because the temperatures are always higher. So the drying, yes, it is there are higher drying rates in the solar drying.
Well, we have a last question, and then after we have to continue. During the test, what was the quantity of dry matters from sludge per meter square per day?
Basically, since this was like a pre-feasibility study, I didn't worry about calculating the exact dry solids that were there. But we started with 0.65% of total solids. And the volume that I've made sure that my volume, the thickness of sludge was 200 millimeters, I think. Yeah, it was about 200 millimeters. So I've kept that volume the same on both tests.
Okay, thank you very much. I think I see that other questions will return there in the discussion session, but now we have to continue, carry on. Thank you, Sabelo. Well, now the next presentation is going to be from our friends from Sanivation, which Sanivation is a social enterprise in Kenya that tries to provide safe sanitation and to communities. So please welcome to Jim Lane, who is going to present us his view, his experience in the watering using the geofabric technology as a sanitation practitioner point of view. Please go ahead.
Yeah, thanks guys, and thanks for all the presentations so far. They've been great, and thanks for the opportunity of presenting this. So again, a kind of a less technical presentation, just telling you our experience of the last 2 years of using this kind of new technology, geofabric textiles to use in the dewatering process. And so I'm basically going to just talk you through the process we have at our site here in Naivasha in Kenya, called Naivasha Treatment Plant, or codenamed NTP. So I'll just run you through the process we have at site, and then our kind of recommendations for geofabrics dewatering technology in the future. Let me just, there we go. So just a really quick process flow of the whole site. So we get our untreated fecal sludge in around between 100 and 120 tons per month in 8 to 10 meter cubed exhauster trucks. And it's mostly from septic tanks. So it's quite a low solids content of around 1%. The sludge then enters the geofabrics, and it stays there for around 4 to 6 days. The solids are then remain in the geofabrics, and the liquids go to a wet well, which is then emptied, and the liquids then go to a wastewater treatment plant and are treated elsewhere. The solids that remain in the bag are then heat treated, which I'll talk about briefly, but won't go into too much detail with that. And then after the heat treatment, the solids are put on a solar drying concrete slab for around 10 days. And you can see, I forgot to say in the corner here, I've got the total solids increasing as we go through the process. And then so they remain on this slab until they get to around 80% total solids, where we then go to our thermal drying flash dryer. This dryer is mostly used for the waste biomass that we mix with the sludge. Mostly, well, we only really get sawdust on site, which we mix with the sludge and then put through the flash dryer, which then has the solids go to 86% or 14% moisture content, which is what we need for our briquetting process. So after it is the sludge and the biomass is at the moisture content that we need, it can then be briquetted, and then we make these, as you can see in the picture here, it's quite small, what we call super logs, which are comparable to firewood. We have a goal to produce around 200 tons of this firewood per month. Current production is around 180 tons a month. But we have lots of success or no problem selling this fuel at a pretty high price. It's been really successful. So now a bit more detail about the kind of drying and the process we have on site. So first thing is the inlet works, and you can see the discharge point here is pretty similar to any other inlet works. One thing we need to do for the geofabrics is add a flocculant. So we add polymer to our sludge. This just speeds up the solid liquid separation process. We found that if we add the polymer, we can get the solid liquid separation process down to around 4 days versus 14 days if we just put the sludge straight into the geofabric without the polymer. This is the polymer dosing options you can have. So like one dosing port or multiple. We have these static baffles on site, which mixes the polymer without any electricity, and we found that to be sufficient, but you can also have mechanical mixing as well. And just a few facts about the polymer we have on site. So treating 120 tons of fecal sludge per, with 1% total solids, you need about 8 kilograms of polymer per month, which is around $80 here in Kenya. So the main thing I'm going to talk about really is this solid liquid separation and the geofabrics. So you can see at the picture at the top here, this is an empty geofabric. It's just like a membrane, and it essentially catches all the solids in the membrane, and the liquids drain out underneath. It's really, really simple technology to understand and operate. There's a picture of it filling up here and a picture of it after 4 days, or 4 to 6 days in the bags. So the facts about our geofabrics and the operations. So 4 to 6 days, as I said, to get from 1% to around 35% total solids. We don't take it out of the bag until we think it's around 35% total solids. Each bag takes around a truckload of fecal sludge, and requires about 8 meters squared of area. And the key thing really about the geofabrics and why we use it at our site is that you don't have to use any sand, or there's no other contaminants that can get into these bags like with drying beds, and that's really key for us as we use it as a reuse product, as a fuel. If we had sand in our final product, it would be a poor grade fuel, and we wouldn't be able to sell it for the high price that we can. And then just a quick thing on CapEx here. As you can see, these are really, really cheap things to set up and install. A bit more about the operations. Once the stuff is dry, you can see these pictures at the bottom here of someone emptying it. It's a very labor intensive process. It takes around 1.5 hours of emptying, and you can see here as well, I've got a picture of the wet well of where it's where the liquid is then pumped to be treated elsewhere. So as I said, I'd quickly mention the heat treatment we do on site. This doesn't really dry the fecal sludge very much. Maybe takes around 10% of the moisture content out of it. But it's a very energy intensive process. So we only use it for heat treatment. We don't really use it for drying the sludge. And these are some options that we have on our sites and previous sites. So really simple, just putting it in like a cooking pot. We found this pretty effective, gets the poo up to a very high temperature, and at that flash temperature where it treats all the pathogens. We have this new technology on site, viscous heater, which works with like some rotating drums and uses the viscosity of the sludge to kind of heat it up and treat it. We've had quite a few problems with this at the moment, and we're still in the process of getting that to work. Long-term solution, how we see operating on our site is doing this flash drying. So the flash dry that we use to dry the biomass that we have on site, we think we could use to treat the sludge. People have done this in the past. We just need to prove that our sludge going through this dryer gets to the temperature that we need it to be. And also in the past at previous Sanovation sites, we've had huge success doing this like solar concentration heating. And so these solar panels kind of direct the sun's heat at a pipe in the middle of the panel there, and transfers this heat into this, you probably can't quite see, it's so small, into this tube here, which heats the sludge. So it's again capturing the heat, the solar power to heat the sludge there and treats all the pathogens. Again, a very simple technology, so I won't dwell too much on this, but after it's been heat treated, we just lay the sludge out on these concrete slabs. And because we need the sludge to be at around 80% total solids before we can put it into our flash dryer, which is what we do next. And then just some key facts about our flash dryer. So we found that we need the sludge to be at around 80% total solids before we put it in this dryer to avoid caking around the edge of the dryer. When it goes through, the sludge kind of sticks to the side if it's not already at 20% total solids, which is why we have the solar drying. And then we only dry it about 6% in this. This is mostly used for our biomass, but it is capable of producing around 0.5 ton an hour. And we're hoping to prove that pathogen inactivation in this process. And then once it leaves the dryer, we put it into our briquetting process, and we make these super logs here, which I said we've had good success at selling. And then finally, just to sum up the technology and our recommendations. So the advantages are no standard contaminants, which is the main thing for us as we reuse this as a fuel product. Really small capex, really simple technology and no power required. Disadvantages, like for bigger projects, you need a much larger surface area, the cost of the polymer, and it's very labor intensive to clean. So our recommendations for this technology in the future, it's absolutely great for what we need. And like any small scale project like this, super great, really good technology. Low capex pilot projects, perfect. Also really great for reuse as there's none of the contaminants, like I said. But I think for bigger projects, it'd be much harder to scale, like at a citywide scale, just due to land requirements and the labor intensiveness of it. Cool. That's everything I had here. I'll leave this page up while people ask me lots of questions.
Thank you very much, Jim. Well, we have a lot of questions, but unfortunately we cannot answer to all of them because we have to go to the next. And then as I told you, at the end, we'll have some spare time to answer questions. So I think here, I have a question that are related. So I'm going to put as one question. What is the name and process of the geofabrics? Do you need to replace geofabrics periodically? Are the geofabrics reusable?
Yeah, I was trying to find the brand name for this. I can't, but it's essentially like it's very similar to the material that you would put down in your garden to stop the weeds going up. So it can be like kind of locally sourced, although we did import it from Europe, like a specific type of stuff. And yes, they are reusable. A lot of people, I've seen these used in other ways where they kind of put it into a tube and they just put the sludge in, let it dewater. It dewaters super fast when they're brand new, like in a matter of minutes for septic tanks and hours for pit latrine sludge. But then they have to cut the bags and they aren't reusable. But we reuse ours, and we've had our current ones on site for for well over a year with no real problems. So once you reuse them, the drainage rate or the dewatering rate reduces to around 30% of when they're brand new. But we would rather do that and pay for the cleaning than have to throw these out every time we need to take in a truck.
This is another question. This is from Mark. Can you explain what is flash drying? And then Monisha M to add, is there any temperature or other parameter to consider during the process?
Yeah, so flash drying is essentially, let's see if I can go back and get the picture up. So we just have here a furnace at the end with a motor on it and a fan. And it just, this furnace gets to around 400 degrees centigrade, and it just blows the hot air through this kind of flash dryer thing here. And then you put the sawdust and sludge in at the edge here, and it just kind of flies through and gets warmed up by the hot air. The dryer at the start is around, or the air temperature here is around 120 degrees Celsius. Which is why we kind of think that it would heat the sludge up hot enough to treat the pathogens. But we just want to prove that this particular dryer actually does that by testing the sludge properly. So we have Ascaris eggs at the moment that we are going to attempt to put through the dryer, and hopefully they're deactivated by the time they come out the end. Okay,
this is the last question for the moment. And it's from Jinson Tanjiwa. And I want to add also something is, what is the calorific value of the super briquette logs? And I'm adding another question, which is, which fuel do you use in your therma and in your flash dryer?
Cool. So the calorific value is a little bit higher than like comparable firewood. I can't remember off the top of my head, but I think it's, no, I can't remember off the top of my head, but I know it's a little bit better than firewood, and that's the big selling point. And people tend to buy our briquettes over firewood if they need their furnaces to burn a lot hotter for a lot longer. These seem to be much better, and also because they have a consistent moisture content, which is why people tend to buy our briquettes over like traditional firewood. And the second question was, what was it? Sorry, I forgot.
And how was fueled your flash dryer?
Oh yeah, so the sawdust we get in for our plant is just waste biomass that would ordinarily be thrown away, like collected from wood production or like furniture factories and things like that. So there's quite a lot of that comes with it, like big chunks of wood or biggish chunks of wood. So we can just put those in our furnace to heat the furnace. And it's generally enough to heat the furnace, but sometimes we don't have enough of that. So we will just use like firewood or maybe even the briquettes themselves, but we try not to use the briquettes because they're worth a lot more than firewood and other feedstocks we can buy.
Okay, perfect. Thank you very much. Sorry, I have to continue to the next question, and to the next presentation. Thank you, Jim. We will continue. There's still a lot of questions that we don't have really the time to answer for the moment. So let's go with the presentation from Yadira Bajon Fernandez. She's from Cranfield University. Dr. Yadira Bajon Fernandez is a lecturer in aerobic process. Yadira's core research area is in bioresources treatment, including anaerobic digestion of waste materials and municipal sludge, anaerobic digestion pretreatment technologies, and biosolids to land. Yadira also does extensive work in wastewater treatment, looking at implementation of lower carbon and low maintenance technologies for small treatment plants and associated value that innovative treatment flow sheets can bring to local communities. Thanks, Yadira, and she's going to present us here about research about the dewatering of fresh fishes. Please go ahead.
Thanks, Santi. Can you hear me now? You see my screen, my slides?
Yes, we can hear you and we can see your slides.
My side. Okay, perfect. Thanks for the invitation, really. So as you say, I'm Yadira. I'm a lecturer at Cranfield. And I want to share with you a project around understanding the watering behavior of fresh species, which is a project that we are doing at Cranfield, funded by the Belinda and Gates Foundation through Duke University, and in collaboration with Melbourne as well in Australia. So I put a couple of slides to, if I manage to go from one to the other, yeah. I put a couple of slides in relation to why we are doing the project, although I'm pretty conscious that it has been mentioned quite a lot, so I will run through this quite quickly. So basically, we all know that in non-sewer sanitation, technologies like pit latrines or septic tanks serve a significant amount of the world population. And eventually these systems require emptying, transport and treatment of the sludge that is being accumulated in there. However, at the moment, it's estimated that only 22% or so of pit latrine sludge is safely managed in an urban setting, which is very worrying if we want to progress sanitation to achieve the Sustainable Development Goals by 2030. So this project is really about recognizing that, as it was said in previous presentations, most of what we transport or we treat later on is really water. So we are recognizing then that solid liquid separation, the watering, is absolutely critical to manage fecal sludge management in certain scenarios. So again, it's been mentioned before. So we all know that fresh species is a valuable resource. And it has potential to constitute a source of energy, fertilizer, and even construction materials, as it was flagged up just a few minutes ago. And there are indeed previous studies that basically quantify the energy potential of fresh species, of dry fresh species, and state that is comparable or greater than many types of wood. So what we also know is that for this potential to be realized, for this value to be realized, we need to dewater the material. We need to get rid of that annoying water. So the question that we have to start with is, we recognize that the watering is critical towards sustainable sanitation, but how much do we know about the watering of fecal material? So if we were to look at what has previously been done, really, there are previous studies that characterize to a certain extent the waterability of fecal matter, and mostly they do so with centrifugation tests, capillary suction time tests, which in reality they may be useful to compare different metrics, but they are really limited in terms of providing us the information and the resolution that we need to be able to model performance of certain mechanical dewatering units and to inform us on how to select those dewatering technologies. So we are trying to address that gap. And the first thing that we did really was trying to develop some methods to characterize the waterability of fecal material. So today really I'm conscious of time. So I'm presenting you almost half of our project, if that makes sense. So we've developed methods for the waterability. We've developed methods as well for characterizing rheological behavior of complex fecal matter of different solids concentrations. So I'm presenting you only the bit linked to the waterability and permeability, but there were some comments before as well about the lack of information of apparent viscosity, rheological behavior linked to fecal matter and to different types of fecal matter. So we've got a strong data set now on that area as well, if anyone is interested beyond the presentation of today, really. So in terms of going back to the waterability in particular, we've developed methods in collaboration with Melbourne University in Australia, which basically allow us to quantify the waterability and permeability. So we are looking at tests like the two that you see here, really. So the first one, it's a shame, this should be a video, really. You see the video now, the excitement of fecal particles settling. So we've identified gel point for many fecal samples, which, as you all know, defines when the feces become a networked structure. And up to this point, we can really use gravity to passively allow solid-liquid interface to reach equilibrium, so to separate solid liquid. Beyond that gel point, we really need additional pressure and some clever design of mechanical systems to the water, the sludge matrix. So we are using this rig that you see on the right, where basically we've got like a very controlled setup where we are able to put our fecal samples and quantify pressure in the cake that we form. So we are able to characterize the waterability at a stepped pressure that is very controlled in ranges that really hasn't necessarily been done before, and to a resolution that hasn't necessarily been done before. So we've characterized for different stool types based on the stool scale, as we all know. We have characterized feces matrix alone, feces with urine, impact of maceration pretreatment. So we really have quite an interesting data set by now. So in the interest of time, I'm almost providing you like a summary of the movie here. I'm giving you the trailer of some of the results that we got. And again, if you want more information, please do get in touch. So some of the initial results that we've got have basically identified that feces dewatering behavior is characterized by quite a long cake formation area, which are very short cake compression zone, which basically says that it's quite a similar behavior to mineral slurries, where we probably all know that we have long cake formation zones with short cake compressions. So this, looking at the results now, it sounds like logical and obvious, but it was not necessarily when we started. I was probably expecting to see something more similar to abiotic or sewage sludge behavior for the watering, which basically has quite a short cake formation zone and a very long cake compression zone. So we're basically saying that the waterability of fecal material is closer to some of the mineral slurries than to some of the sewage sludge. That is what we probably expected to start with. We've looked at aspects like compressive jet stress, of various fecal stool types, feces with urine, without urine, macerated materials. And what we are basically saying, and you have here this graph where we have an example of wastewater material, different fecal matter. You've got a macerated sample and we've got a calcium carbonate, just for the sake of comparison, really. And what we are saying is that feces can compress to a much higher solids concentration than wastewater sludge until the network structure is broken, which is the mechanical limit that we have in the watering processes. So we haven't seen major differences between different Bristol stool scale type of feces, but we've seen quite a significant difference when we macerate the sample. And we are doing quite a lot of work now trying to characterize what exactly is maceration doing to our matrix. So macerated pretreatment facilitates a homogeneous matrix and promotes even higher solids concentration to be reached at compressive jet stress. So again, you will see here that some of the implications are really quite impressive. So when we are talking for maybe for wastewater sludge of a volume fraction of 0.2, we are relating that to close to 0.4 to 0.3, depending on the type of fecal matter that we are working with. But it's a significant difference that we are observing. In terms of how this compares with wastewater sludge, as I say, feces can dewater to a greater extent than wastewater without an addition of polymer. And we observe that the gel point is actually 5 times higher than for wastewater sludge. So we are saying that we can achieve passive sedimentation up to 10% total solids. And when we start looking at different pressures, we can reach concentrations in the water cake up to 50% total solids, which is again quite impressive when we link it to many of the presentations that you guys have just done in terms of drying being a facilitator of value recovery downstream. So we are trying to we're achieving some of those concentrations with mechanical drying, which is again quite impressive from a data point of view. In terms of the rate of the watering, so here you've got a graph that many of you will be probably familiar with. So we are looking at hindered settling function, which is the inverse of permeability. And as with compressibility, what we are seeing is that feces of various stool types and feces with urine are more permeable than wastewater. So you've got this line here. I'm hoping that you guys can see my mouse now. So you can see this line of wastewater, and you can see this line here of calcium carbonate, again representing a mineral slurry. And what we are seeing is that fecal material is somewhere in between the two of them. In this case, maceration has a small impact, but really not as much. So maceration seems to impact to a greater extent the waterability than permeability. So trying sort of not to show you absolutely all the data sets that we have and drawing some conclusions in the 10 minutes I have. So I think the main key outcomes that we have here is that feces exhibits a similar dewatering behavior to mineral slurries when we look at the waterability. So soil compression zones, as opposed to what we see in sewage sludge, for instance. We are able to reach concentrations with passive sedimentation of around 10% solids, which is the yellow point that we have identified for fecal material, which is again around 5 times greater than what we observe with wastewater sludge to start with. We can reach compression at higher solids concentration than for wastewater sludge, and we've achieved, as you've seen, solids concentrations of 50% with mechanical dewatering again. And feces are generally more permeable, somewhere in between wastewater and mineral slurry. So still, what we're trying to do with this project basically is developing the underpinning science that will allow us to choose the technology and have a decision platform based on the matrix that we have for selecting one or other technology, and whether that looks some of the big boys that you have here on this slide, or more linked towards designing some of the other technologies that were discussed this morning. As I say, I don't have really time to enter into that other second part of the project, but I want to share with you just quickly some of the things that we are seeing. Sorry, before entering into that, I guess just trying to put into context some of the implications of what we are seeing, really. I said that not necessarily everything that we've seen is what we expected to see. So fresh feces contain easily 80% BS, volatile solids, and a significant fraction of proteins and carbohydrates, which generally have been associated with poor dewatability in wastewater sludges. Still, we are seeing that fresh feces exhibit a dewatering behavior that is really characteristics of mineral slurries rather than biotic sludge. So we are seeing the matrix is much more amenable to the watering than we necessarily expected to start with. So we are currently hypothesizing really that the colon is already doing quite a lot of the job, and that the EPS network structures from bacterial biomass, they don't have sufficient time to form when we get the fresh sample. So we are hypothesizing that this will change if we are working with aged feces as opposed to fresh feces, which is what we use on this particular project. Which means that if we prove this to be true, we are really quantifying the penalty that we will have if we don't dewater immediately at source, if we transport that material and later do the solid liquid separation. So we are now trying to extrapolate the methods that we've done, that we have applied to our fecal material, and do that for aging feces. In terms of other data sets that I said we are happy to provide to share with you guys, obviously in a different context. We have developed methods for the watering, but also for rheological properties of different fecal material, and there's some interesting results that part of them align with what has been presented before in terms of characterizing the sticky phase, and we've done the resolution of that, as you see in this little graph here, for different Bristol stool scale types. And it's quite interesting to see how all of them really behave the same. And the major differentiator between different feces is really the solids content. We are also looking at things like a structural recovery. So this basically links to the deformation that the sludge matrix has as a non-Newtonian fluid and schizotropic material when we apply certain amount of energy or power, meaning that at some point when we left the fecal material to rest, the material recovered its original structure, but in some others it doesn't really. So in some cases, even if we leave the matrix 24 hours, we still have a lower apparent viscosity than we obtained originally. So it's starting again to link all the picture together and letting us build into that decision platform that we're trying to develop at the moment, of which technology to choose, but also when to the water, and what are the real implications of things like maceration in the matrix that we are working with. So watch the space. There's quite a significant data set behind these graphs. I mentioned that other data that we are looking at, but I cannot really share with you today. So if you guys want to, any of you want to get in touch, you've got my details there. As I say, this is just a bit of a trailer of the movie, but we've got quite an interesting data set behind this that it would be very interesting to chat with you about. So that's from me, Santi.
Thank you, Yadira, for your interesting presentation and to show us the interesting work to characterize the watering of feces, fresh feces. So I don't know if I was going to see if there is questions. Somebody wants to talk, or there is no questions concerning this presentation. No. Yes, there is one. Yes, there is one from Rita El Jahar. What are the dewatering technologies that you have tested, and were there any optimal conditions for high efficiency?
So at the moment, this is something that probably I can answer in a couple of weeks, really. So we've basically developed all the dewatering tests in this control step pressure rig that I mentioned. And what we are trying to do now is to model the efficiency of different dewatering technologies based on that. So, I mean, the model is really on its way. So we are developing models for the standard technologies that you can think of, like from centrifuge to belt presses, the standard technologies. And I will be able to answer that as soon as the model is finished. So I guess if we get in touch in a couple of weeks or so, I'm probably able to answer that question a bit more, Santi.
Thank you. So, well, we have, well, there is missing 15 minutes with the presentations are finished, and we have 15 minutes before to close the first session of the workshop. So I would like to know if, well, there are some questions that I promised that I'm going to answer from my presentation. Let me check them. Here you go. It's Dr. Mustafa Sene. Hello, Dr. Santiago, for the presentation. What is the optimum energy consumption range considering your recommended 30% dry moisture content to not exceed? Well, it's the value that I said is it's measured in laboratory measurements of the heat of drying, the energy that is consumed in drying. And well, the energy is stable until approximately 30%, 30-40%, and then start to increase like exponentially because it's very bounded. So it's difficult. I mean, this, as I told you, there is to evaporate 1 kilogram of moisture, you will need approximately between, well, roughly 4,000 kilojoules per kilogram. This is very roughly. Between 4 and 5 mostly. So, but this is just considering the thermodynamics of the system. And then for sure there is in the process, there are going to be loss of efficiencies, there are going to be performance parameters that we have to include. So it's difficult to answer this question like this, but it's, at least we can determine how is the minimal energy that we can get it. I hope that this will have answered your question. And then we have somebody have another question from Jill Froll. What is the effectiveness of drying fecal matter at the point of production user interface? Well, the effectiveness, I would say that it's that if it's dried in situ, we remove moisture, we remove weight, and we remove volume. That sometimes we're reducing costs. We're reducing costs of transportation. So we manage to dry the sludge in situ, which is the ideal case. When we transport it to the place we're going to continue to treat it or reuse it, there will be much lighter. So for sure, it will use less fuel and less less transportation will be needed. Then I have one last question from a presentation, which was from Ananta Murthy. Can please reiterate about the water activity parameter and its effect on moisture content and drying time, please? For sure, well, water activity is quite complicated thermodynamic parameter, but I think it characterizes quite well how the moisture or the water is linked with its environment in a given media, in a given solid or solution, etc. Water activity is defined as the vapor pressure of the water in this environment to the vapor pressure as pure water. So sometimes, usually when the water is linked to its environment in some way, some physical or chemical or biological interaction, then this will reduce the vapor pressure of the water, and so the water activity will decrease. If it's not linked to its environment, that means that it's unbounded. So with this, we can, it's just an indicator of how the moisture can be linked, bounded in the sludge, and in its value, if it's close to 1, it's because the water is not very bounded, but if it's close to 0, that means that the water is really bounded. So it's just give a good indication, and for sure, more is bounded, and more is going to be difficult to dry, because we have to break to dry it, you have to break the chemical interaction between water, but also between water and the compound with which is linked. So you will have to bring more energy, and also it will be a slower process also. So that's okay. So I don't know if there is, I think we have to, there is 10 minutes left. I don't know if somebody wants to add some other questions. There's a lot of more questions for Jim, but I think what we can do is I can give to, if Jim agrees, I can send the questions to him, and Jim will answer them by his computer, and we will share with the group. That we can do, because now the last 10 minutes, I would like to conclude. And just I would like to see if Patricia and Leonard. Sorry, there is somebody. Somebody has his micro on. Yes. So just to finish, I would like just to see if Patricia and Leonard and Angelique can give us her how they see the session today, and just a small debriefing of 2-3 minutes. What did you learn, and what advices can you tell us concerning what you heard today? And if you can do that, please. Maybe we can start with Patricia.
Okay, thank you, Santiago. So thank you very much for all the presentation. It was really very interesting, and we have received a lot of information. For me, as you know, I'm working on sewage sludge drying. So I don't know the materials, and I have surprised to discover that the behavior is finally very different from what we know for sewage sludge. So that's very important for us. So I think that one main issue concerns the structure of the materials, in able to understand at the end the mechanisms involved in the different separation operation. I'm really impressed by the result achieved with the geofabrics, because 35% total solid is quite high for gravimetric separation. So I'm really impressed by this results. And of course, solar drying is a promising technology for dewatering this kind of materials, but I think that there is still a lot to do, even for sewage sludge, of course, for optimizing this kind of process. So that's first comments from my side. I will try to work a little bit for tomorrow.
Thank you very much, Patricia. Thank you very much. Your input is very appreciated. And Angelique, if you can say what you can say to us, based on your experience in sewage sludge and what you heard about today with fecal sludge.
Yes, I would say that I let's say will more focus on perhaps the common points between your product and sludge, because there are also some similarities, and of course the techniques that can be applied I think are quite similar, and I think there is, let's say, a way to learn from, let's say, the two different types of materials. And in that sense, I was very interested by the last presentation coming from Cranfield, because there is still this, let's say, this lack of knowledge in link with the composition of the sludge. But I was very interested by the last slide, and also by the EPS contents related in the effect on the dewatering, that it could be, let's say, an idea to dewater, let's say, as soon as possible the feces to have, let's say, a better behavior. But this question of EPS is still at the heart also of wastewater sludge, and I think that let's say a better knowledge in that domain, either related to your material, but also in the context of sludge, could be also of interest. And the same for what is linked with rheological properties versus, let's say, a composition and so on. Yeah, so for me, it was a very rich. Of course, I learned a lot about your materials, but also some, let's say, a common thing between the different domains. So I find it very interesting. And so I hope some perhaps collaboration could emerge from that in the future. So thank you.
Thank you, Angelique. Thank you very much for your input. So yes, with this, I will, if there is no comment from the audience, I will consider that the session of the day is closed, and I hope to see you tomorrow. And my point of view was very interesting to hear these presentations, to see different process from the watering until drying, and to see study different technologies at different contexts. We see the case of sewage sludge, and we see the fecal sludge with his similarities and his differences, and also we're going to study the physics, which is the elemental component from that the fecal sludge, and also sewage sludge, but has been already quite transformed in sewage sludge, but basically there is a lot of there. And so yes, it was very interesting to hear all these presentations. I think I'm going to conclude this session. We learned a lot. We received a lot of information, and I look forward for see you tomorrow and to continue with these further presentations and further discussions. Thank you very much, and I wish you a nice evening for the guys from this side of the world, and good afternoon for the guys in America, and good evening, I think, in Asia. Thank you.
Thank you, sir.